All right. Sorry, I was never good at coloring inside the lines. I had written down the questions here and realized you probably need to see what formic acid is. Here's formic acid. It's very sloppily drawn as usual. I'm sorry. You have a carbon, which is double bonded to an oxygen. So that's what that's supposed to show you there. That oxygen is going to have two unshared pairs of electrons on it as well. Those are not always shown. You just have to know that they're there. That carbon also has an oxygen, which will have two unshared pairs. And in turn, that oxygen is bonded to a hydrogen. And just got lazy about drawing a bond line in between there. When you get to organic chemistry, that kind of goes away. You just say OH and don't worry, you know there's a bond between the oxygen and the hydrogen. And then over here is where I ran out of room. So here's hydrogen. So anyway, this right here, C, you'll see it written sometimes as CH2O2. You can see it as HCOOH. There are several different ways it's written, but this is the structure. All right, so this stuff is called formic acid. The word formic comes from the Latin word for ants. And that's because when an ant stings you, this is what they inject. And that's what gives it that burning sensation, is this acid. Now this is an acid because this hydrogen, the one bonded to the oxygen, will come off and leave its electron behind, which means, of course, it comes off with a positive charge. That leaves a negative charge behind here on the oxygen. That negative charge does not have to stay on this oxygen because then the negative charge and the unshared pairs and the double bond pairs are able to move, which is something that we've talked about very little. It becomes very important in organic chemistry, and it's called resonance. It's where instead of a double bond up here and two unshared pairs and a single bond down here with three unshared pairs, again, I didn't show that, probably should have. So instead of a double here with two unshared pairs and a single here with three, they will move. So one of these unshared pairs will move in to form a pi bond, and the pi bond up here will move out to become another unshared pair. And by these moving back and forth, it's sort of like, I use the analogy of if you have to carry a heavy object a long distance, you don't carry it in the same hand all the way. When that hand gets tired, you switch it over to the other one. So this negative charge doesn't have to be carried by just one oxygen. You can shift things around and carry the negative charge on the other oxygen. And that, being able to give one oxygen a rest, so to speak, stabilizes the situation. Okay, more about that than I ever really intended to say, but these are all important topics. Okay, so another insect that creates formic acid and will spray it at predators is a type of beetle. The carabid beetle. And it turns out that the formic acid solution that the beetles squirt for defense is 0.04 molar. So the question here is, what would be the pH of 0.04 molar formic acid? Now they give us a Ka value here for formic acid. Ka is 1.77 times 10 to the negative 4. So, formic acid, this, COOH2, most commonly you would see it probably written as HCOOH. And again, H comes off. It's this one over here, which would be this one here in the way it's done in organic chemistry. So that's going to donate this proton over to the water, and that will produce reversibly, of course, hydronium and HCOO negative. Now, if this is formic acid, okay, formic acid here, what is this? This is its conjugate base, which would be called, who said that? Yes, formate. Okay, formate. That's the conjugate base of formic acid. Cb, conjugate base. All right, so this is initially 0.04 molar, and these are, of course, initially zeros, and this is going to go down by x, and these will go up by x. So we'll have x of each of these, and still essentially 0.04 of this at equilibrium. I hope I don't have to write out that entire ice table for you here, because I'm not going to. So we've seen enough of these now. We know that the Ka of 1.77 times 10 to the negative fourth is going to equal x squared over 0.04. All right. So now we're going to multiply both sides by 0.04. That'll cancel it out on that side. So we need 1.77 times 10 to the negative fourth. And we are going to multiply it by 0.4 times 0.04. And that's going to give us that. 1, 2, 3, looks like 5 zeros, so 7.08 times 10 to the negative sixth. And then we're going to take the square root of each side, so we'll get the square root of that. And that's 2.66 times 10 to the negative 3. So x is 2.66 times 10 to the negative 3. All right. Now what does x represent? X represented hydronium here. That's the ice table that I skipped, but we've seen that same thing over and over and over, so I hope you're okay right here. X represents the hydronium. So if we take the negative log, so the negative log of 2.66 times 10 to the negative third, which is going to be somewhere in the ballpark of 2.6, 2.7. Let's do the log. And we now need the negative of negative 2.57. So that equals the pH, and it equals 2.57. I went too far off. I said 2.6. 2.7 was off a little too far, but oh well. Okay, so that's what we get. The pH of this is 2.57. Now, we haven't done many degree of ionization questions, so let's do that. The degree of ionization, we're going to take this number and we're going to divide it by the original amount. So we divide that by 0.04. 64.3. Something doesn't sound right about that to me. Know exactly why that doesn't sound right. I said it backwards and then did it backwards. You need to take this and divide it by the 0.04. And so I did it the other way around. Is that what I did? I don't know anymore. Times 0.04. Let's see if that takes me back. Yeah. Interesting. Funny how that turned out that way. So 2.66, I think I know now what I did. Times 10 to the negative third. And we need to divide that by the 0.04. Alright, and that's 6.6%. That's actually just a little bit high. Remember, we want this to be under 5%. But still, we take this and we divide it by 0.04 and then multiply by 100, and we get a 6.7% ionized for the degree of ionization. Well, the percent ionization. The degree is the 0.066, this number. Okay, now I wanted to show you something new. That, of course, is just another example of something we've done, finding the pH of an acid when we know it's Ka and we know its molarity. We do a lot of that. But I wanted to show you what would happen. And we see that this ionized 6.7%, but that's just in water. Okay? What if we put that formic acid into hydrochloric acid? Okay? So what will the degree of ionization be for this same acid if it's dissolved in 1 molar hydrochloric acid? Instead of putting this in just in water, let's put it into hydrochloric acid. Okay? So now, what do we know about hydrochloric acid? First thing I want you to say is it's a strong acid. Okay? And since hydrochloric is a strong acid, what do you know about it? What does that mean it does? Strong acids ionize completely. So when HCl is put into water and it forms hydronium and chloride, how much hydrogen chloride remains? If it starts at 1 molar, and this starts at 0 and this starts at 0, how much does this change? How much of that 1 molar ionizes? The answer is every bit of it. So how much of it is left at equilibrium? 0. So if this goes down 1 molar, what does this do? This goes up 1 molar, and this goes up 1 molar. So how much hydronium is there? 1 molar. Yes, there's 1 molar chloride too, but we don't care. We're worried about hydronium. All right, you with me? Strong acid, 1 molar. Ionize it completely. All of it goes away to 0. Since one of these makes one of these, we lose the same amount over here and we create 1 molar hydronium. So we're going to take this HCOOH, we're going to put it in water. It's going to make hydronium. It's going to make HCOO negative. Sorry. Sloppy, plus HCOO negative. Same thing as up here. Okay. Looks much neater right there. Initially, this is 0.04. Is this 0 though? Because we didn't just put this into water. We put this into water that contains what? 1 molar hydrochloric acid. What did that 1 molar hydrochloric acid do? It ionized completely. So how much hydronium's already in the water before we ever add the formic acid? It's already 1 molar. Now, there's no formate yet. Now this changes. This goes down by X. This comes up by X. This comes up by X. So that at equilibrium, we have 0.04 minus X. Same thing. But here we have a difference. We've got 1 plus X. And here we've got X. Okay. I'm going to stop for a minute to let you think about what's happening. Up here in blue, we calculated the molarity, the pH and the degree of ionization, the percentage ionization of this formic acid in pure water, where there was no hydronium to begin with. Down here, though, we're putting it into not just water, but water that has hydrochloric acid already in it. And the hydrochloric acid is 1 molar. And it ionizes completely so that there's none left. And that means that there's 1 molar hydronium produced. So there's 1 molar hydronium in there already. Initially, there's already 1 molar hydronium. So let's see what that does to our calculations. The Ka for formic acid does not change, 1.77 times 10 to the negative 4th. But now it equals 1 plus x times x over 0.04 minus x. Now what do we do with x's that we're simply adding or subtracting because they don't really make a difference? We just ignore them to make the math easier. So that plus x, we're going to ignore that. Alrighty. So now what happens? 1, and ignore the plus x, so this is just 1 in here, times x is simply x. And we need to get rid of this 0.04 down here, and we're ignoring the minus x because, again, it's not enough to worry about. So we've got to multiply this number times 0.04, and that's just going to equal 1x. So 1.77 times 10 to the, what was it, negative 4, 4 negative, times this 0.04 down here, 0.04, equals that. We have 1, 2, 3, 4, 5, so it's 7.08 times 10 to the minus 6. 7.08 times 10 to the minus 6 equals x. Now, what is that divided by the original 0.04? Divided by 0.04. 0.000177. In other words, 0.017%. 0.01% ionized. Ionized is much, much less. Up here, it ionized nearly 7%. But in the presence of a lot of hydronium, it only ionizes 0.017%. Now you can think about this in a couple of ways. For one thing, go up here, we have this at equilibrium. And at equilibrium, it does this much. But by adding hydronium, Monsieur Le Chatelier, what do? When we put something extra in on the right-hand side of the equation, it shifts to the left. So the amount of hydronium being produced by the ionization of this formic acid is driven back to the left pretty significantly. So we only produce this much more hydronium. Okay? So now what would the pH of this be? Now, there's 1 molar hydronium already there from the hydrochloric acid. We're going to add this much more hydronium from the formic acid. So, let's see here. 7.08 times 10 to the negative 6th. That tiny little amount of hydronium being produced by formic acid trying to ionize. But Monsieur Le Chatelier is saying, well, I'm putting more stuff right here, and that's going to drive your equilibrium back to the left. So anyway, we only get this much, and we add that to 1. So plus 1 equals that. Now, how do we find the pH? This number is this 1.50708. This is the amount of hydronium ion. So we take the negative log of that. So let's do the log. And let's make it negative. And look at that. It's a negative number. It's slightly, very slightly below zero. Negative 0.000003075. The pH is less than 0. And yes, that is possible. pH can go below 0. So, this is something called the common ion effect. Common ion effect. What that means is the ionization of formic acid produces the hydronium ion. When mixed with hydrochloric acid, which also produces hydronium ions, hydronium is what these two acids have in common. Hydronium is common to both. Ionization of hydrochloric acid produces hydronium. The ionization of formic acid produces hydronium. And so the common ion, if they're both producing it, neither produces as much. Now the impact on the ionization of hydrochloric is going to be negligible because it's a strong acid. It ionizes completely. But you can see, you can see that it had a really big impact on the ionization of the weak acid, the formic acid. One last thing about this. I just may have blown your mind by saying yes, pH can go below 0. Okay, so let's go right over here and I'll write in green to make this stand out. Hydrochloric acid. Okay, looking at it over here, when it was 1 molar and it ionized completely, how much of it breaks down? All 1 molar of it, so there's none left. Concentrated hydrochloric acid comes in a 12 molar concentration. So I'm not even going to go with that. I'm going to go with something a little more watered down than that. Let's imagine 10 molar hydrochloric acid. So if 1 molar hydrochloric acid leads to 1 molar hydronium, what will 10 molar hydrochloric acid lead to? If this is a 10, all of it ionizes so that there's 0 left. If it ionizes completely, right? If it's 10 molar, how much hydronium will there be? The hydronium would be 10 molar. Hydronium ion concentration equals 10 molar. 10. That's the hydronium ion concentration, right? What's the log? It's 1. What's the negative of that? Negative 1. So concentrated hydrochloric acid has a pH lower than negative 1. Just for the fun of it, it's 12 molar. Concentrated hydrochloric acid. I went with the 10. Now let's do 12. What's the log of that? 1.079. And of course, to find the pH, you want the negative of that. So negative 1.079, negative 1.08. So yes, pH can go lower than 0. Lower than 1, lower than 0. It can go into the negatives. That's probably, I don't know, sulfuric acid could probably go lower than that because it is, number one, it's diprotic. It gives off 2 hydrogens. And also it is available, its concentrated form is 18 molar. So if you took 18 and even if it only gave off 1 of its 2 hydrogens, then it could create a pH of negative 1.26. And it can go a little bit lower than that because some of the second hydrogen of sulfuric acid also comes off. Okay, 24 and a half